Okay, so the last lesson we looked at and started to learn how to do some nomenclature. The IUPAC nomenclature for organic compounds says, because organic compounds have their own way of being named, and so we're going to continue with that to see how to actually name some compounds, and we're going to stick to sort of simple things for the most part. So we'll be talking about alkanes, alkenes, alkynes, and some carbon chains with substituents on it, and how you determine how to name these. So first of all, the beginning of this is when you're naming a compound, you name it according to its root, its suffix, and a prefix. Now, the root is the longest number of carbons in a continuous chain. Okay, the number of carbons. So maybe you have 8 carbons in your chain. That would be an oct something. All right, maybe you have 7, a hept something, or maybe you have 2, an F something. So you've got to remember those names. And then we end it in the type of chemical it is, the type of organic compound. And so we've seen how to name anes, and the double bonded enes, and the triple bonded ines for hydrocarbons. So we could have a triply bonded butene. We could have a double bonded hexene. All right, and the prefix, which we haven't really worked on anything, tells us what the substituents are. So it tells us substituents on that chain. Instead of having a hydrogen as part of the bond, there will instead be some carbon chain. All right, and we've looked at those. Those were the alkyl groups. And we're going to come back to this, but you should look through your book and understand all of these rules. But we'll look at them again when we get to the end. So here are these roots that you should have memorized. Meth, it has 1 carbon. Pent has 5 carbons. Hept has 7 carbons. And then you name it at the suffix according to what kind of chain it is or what kind of organic chemical you're talking about. So we're going to talk about constitutional isomers. Okay, those are structural isomers. Isomers means they have the same molecular formula. Okay, but they're arranged differently in the bonded atoms when they're constitutional or structural isomers. And when they're structural isomers, they have different physical and chemical properties. And so we looked last time at the butane. Butane, remember, has 4 carbons, and the ane indicates that it's all singly bonded. So the hydrocarbons here, this is the expanded view, which you would start by learning to do this. But once you've got that down, then you would use this kind of a view where you'd say 4 carbons with all the hydrogens needed to make it the carbon obey the octet rule. And then here's that structural formula that we the skeletal formula we looked at, which we're not really going to spend a lot of time at. But notice that at every curve, at every turn, you have a carbon and however many hydrogens it takes to give a valid Lewis structure on every carbon. And so that would be just a straight chain. Whoops. Go away. That would be just a straight chain. Even though it bends in space, this would just be a straight chain. But we also saw that we could have something called 2-methylpropane. All right, so we have a 3-carbon chain, 1, 2, 3, And when we have the extra, this is still C4H10, just like the one above it, only it's not the same. Now instead of having 4 in the longest continuous chain, we have 3 and a substituent. And I want you to notice that the prefix tells us that we have a 1-carbon group attached to our 3-carbon chain. So it's a methyl group, and in this case, this methyl is bonded to carbon 2. So 2-methyl propane. All right, that's how you're going to name these kind of things. We've looked at those before. What about these isomers, pentane isomers? We haven't really seen pentane. We didn't work with it specifically, but you should go through this example in your book. Here is the 5-carbon chain, just a straight chain, so pentane. Now, what are the structural isomers on this? I'm going to go down, I'm going to make the chain 1 carbon shorter after I finish that, so that's going to give me 4 carbons. Okay, so a butane, and then I'm going to make a substituent. Okay, all I have to do is add, for example, this methyl group. That's a substituent. It's methyl because it just has 1 carbon, and it's numbered in such a way that it gives the lowest possible numbering to the methyl group. And so in this case, we'd say 1, 2, 3, 4. You should number your carbons always when you're doing these kind of more complicated structures. And then you can see that your methyl group is on carbon 2. What if, instead of drawing it this way, I made this structure with the methyl group on what appears to be the next carbon over? Would this be a 3? Is that a 3-methyl propane? And the answer is no. I want to number this with the least possible numbering. And so even though it's not normal for we Americans, we would go backwards here. 1, 2, 3, 4, because my methyl group is on the, I want to number it in such a way that it's on the lowest possible numbering. And so you'll see that these two are actually the same. They're not different. Or it's just that the molecule, which it can easily do, is flipped in space the other direction. Now I'm going to go down 1 more carbon, okay, on my carbon chains, and I'm going to see that there's 3-carbon chain for propane, all right, and I can put 2 methyl groups, each on carbon 1, 2, 3. And I'm still going to get C5H12. And so in this case, notice that I'm telling you where both are. Both of those methyl groups are at 2. So carbon 2 has methyl 1 and this methyl, so 2, 2. And then I have to say how many methyls there are. And so 2, 2 dimethyl propane. Dimethyl propane. So let's go up. Let's go through some of these hexane structures. Up 1 more carbon. So carbon with a chain with 6 carbons, straight chain, is a hexane. Let me number these. Got to get in the habit of numbering them anyway. 1, 2, 3, 4, 5, 6. Perfect straight chain. Now, how do I decide if there's more constitutional isomers? I'm going to go down 1 on my carbon chain. Okay, so I'm going to have 5 carbons now instead of 6, and I'm going to look for substituents with the methyl groups or ethyl groups, but right now just methyl. And so I can make this a 2-methyl group, pentane, 2-methyl pentane. Now this looks like it might be 4-methyl pentane, right? I mean, if we number 1, 2, 3, 4, 5, that looks like it might be a 4-methyl. But remember, we always give it the lowest possible numbering. So we start backwards here. 1, 2, 3, 4, 5. All right, so now with the lowest possible numbering, I can see that my substituent is on carbon 2, and that substituent is just 1 carbon, so 2-methyl, not 4-methyl. Now I can also move my substituent down 1. All right, so in this case, this would be from either direction, 1, 2, 3, 4, 5, whichever direction you go. Oops, that should have been subscripted. This is a methyl group on carbon 3. I could also do it, the numbering, in this direction. It doesn't matter in this particular case because both of them end up on the 3-methyl pentane. But your goal is to always look for the lowest possible numbering, so you always count forward and backward, whichever way works the best to get the lowest possible numbering. Now, remember, I can't make something called 4-methyl pentane because if I move it down 1, we just did this. If I moved it down 1, then it's still just 2-methyl pentane. So that one doesn't work. That's all I can get on there without changing anything else. So I'm going to go down another carbon now and see if I can get more substituents. As a matter of fact, I can. So now I have a 4-carbon chain. 1, 2, 3, 4 carbons. All right, and I look and see that there's a substituent at carbon 2 and at carbon 3. Both of those are methyl groups, just 1 carbon. And so I'm going to say it's 2,3-dimethyl because there's 2 methyl substituents on the chain, dimethylbutane. So, is it possible for me to have others? Well, we're not really going to deal with the cyclic structures, but we could also have cyclic structures. And so I'm not really going to expect you to be able to identify cyclic structures, but we could still have another 1 or 2 of these hexanes or these C6H14 molecules. So we can come up with a few more. For example, we might do, how about 1, 2, 3, 4. Oh, I am at butane, so I want just 4 carbons. And let's assume I put carbon on both the carbons on at one place. I would number this 1, 2, 3, 4, and these are going to be substituents. When you put in all the hydrogens, you'll see that this has got 14 hydrogens, and you would name this again 2, 2, a little mark, dimethyl butane. So I didn't really get anywhere by changing that. Oh, yes, I did. Can I do 3, 3? Is there such a thing as 3, 3-dimethyl butane? And the answer is no, because if I move them down to this, for example, here, let me redraw this. Let's assume for the moment that I put them here. Well, there's nothing different about this from this. All I've done is turn it in space. We would number this 1, 2, 3, and 4. Can I make an ethyl group? So instead of having 2 methyl groups, how about if I put a group on here that's an ethyl group? For example, maybe I can make 1, 2, 3, 4. There's my butane chain. And then I'll have an ethyl group that has 2 carbons on it. Is this going to be an isomer? Well, the answer is no. All right, and why? Because I haven't counted my longest continuous chain. I might look and think this is 4 carbons long because it's in a straight line, but I would be all wrong here. because I have to count my carbons in such a way that I can find the longest continuous chain, the longest. And so I might count 1, 2, 3, 4, 5. 5. And if I'm looking at this as this is the substituent, right here on a carbon 3, this works out to be 3-methyl pentane. Now, what I want you to recognize out of this is that carbon chains turn. Carbon chains turn in space. Carbon chains rotate so that they can flip on the backwards and forwards. And so we might have, for example, some kind of a pentane molecule that starts here, goes there, and then comes up here. I still want to, let me get this in the right place. I still want to number this chain the longest possible way. So if I count here, that's 3. If I count from here to here and use this as a substituent, that's 4. But if you'll look at this, oops, well, I erased it. If you'll look at this, we can number this 1, 2, 3, 4, and 5. All right, or we can number it. Oh, that's the only way we can number it the other direction. But if we come out here and try to make this 1, 2, 3, then we have not gotten the longest part of the chain, because the longest part of the chain includes all of these carbons. Okay, now what if we're given a name and we're asked to draw our structure? Well, if we know it's a hexane, so start with the root and the type of organic compound it is. So we know it's a singly bonded because it's an ane, and it has 6 carbons. So let's get 6 carbons on here. 1, 2, 3, 4, 5, 6. And then I want to make 3-ethyl 2-methyl. Now, why is a 3 in front of the 2? Because when you're naming these, the substituents are named alphabetically. It's not the number, it's the substituent. And so ethyl comes before methyl. So it's named according to its alphabetical order. All right, so let's see. Let me number. I'm going to number backwards just for fun, just so you can see. This will be 5 and 6, and therefore I'll have a ethyl group, CH2, CH3, on carbon 3, and on carbon 2, I'll have a methyl group, CH3. Now, before I go on, I want to look and see, did I change anything? Do I still have hexane as the longest possible chain? Well, in this case, I might get a different color. I might want to number 1, 2, 3, 4, and 5. And in that case, that's not the longest possible chain, so this is a good structure. I like it just like that. And then, of course, this is also 3-ethyl 2-methyl, only this time I numbered 1, 2, 3, 4, 5, and 6. What if you saw a structure, so where it was like 1, 2, 3, 4, 5, 6. Okay, so there's a hexane with 6 on it. And then we're going to have an ethyl group, CH3, CH2 here, CH2, and a methyl group here. You would still want to go through and check what's the longest chain. If you draw it, well, you probably know. But if you didn't draw it, then you need to count, all right? You might try and count this direction, 1, 2, 3, 4, 5. Well, that's good, but keep counting because this might be 1, oh, no, I want to have the substituents on the lowest possible, so 1, 2, 3, 4, 5, and 6. All right, so remember those molecules, those straight chains can turn in all sorts of directions. So, now, here's a molecule. I want you to take, a minute or two and try to make the name out of this thing. Try to figure out what this structure's name is. So, I don't know. Give you a minute and a half. All right, so let's look at this structure. Maybe you'd like to fill in all of the carbons. All of the hydrogens. So at the end of the chain, you know those are going to be 3 hydrogens to make that fulfill the octet rule. Now let's look at this one. This isn't just an H because this carbon has already had 1, 2, 3 bonds, so it can only just make 1 more. And this one would make 2 bonds to hydrogen, so would the next one. So remember those methylene groups are just CH2 units. Now on this one, I'll have to have an H2 in here. What about this carbon? This carbon is already bonded to 1, 2, 3 carbons, so it can only take 1 hydrogen. All right, so now that is our structure. What is its name? What is its name? All right, the name. Well, we want to number so that the substituents get on the lowest possible numbering of the chain. So let's count. 1, 2, 3, 4, 5, 6, 7. So we might call this a heptane. And then we'd have, this is a substituent, 2, wait, am I going to be able to do that alphabetically yet? No, but this is a 2-methyl. I need to think about how to do this alphabetically. And then here I've got a 2-carbon group, and it's on carbon 6. 6, and we'll call that ethyl. And so you'll go to all this work, and you'd come up with a name, and you'd be wrong if you do it this way. Because I did not look for the longest continuous chain. The only thing I did right there was I counted the carbons in the straight chain that I'm looking at, not all possible numbering. And so, let me erase these because they're not right. Now, I'm still going to call this 1 because I can see that I have a substituent here and I want to have the lowest possible substituent. 2, 3, 4, 5, 6. Now, here's a dilemma. This is not a substituent. It's part of the chain, 7, 8. So you can see I have actually in my chain, even though it flipped and turned in space, I have 8 or an octane as my root and suffix. Okay, so octane is my root. Now I need to number. And so I know there's a methyl group on carbon 2, and there's a methyl group on carbon 6. So I would call this 2,6-dimethyl. I need 2, the di, to indicate there's 2 methyl groups, and they're located at carbon 2 and carbon 6. All right, let's try this one. Again, I'll give you this time about a minute here. I want you to look at and figure out how to name this structure. All right, so our first task is to find the longest continuous chain. So we might say in our straight chain, 1, 2, 3, 4, 5, 6. So we might be tempted to say 6. But that's not correct because we can keep counting, and so you should keep counting all the time. 1, 2, 3, 4, 5, 6, 7, 8 in this part, if I go through here on this part of the chain. And then I have some substituents. I'm not done. See what else I can do here. Another way I could number it. Darn it. Another way I could number it. I think it was down here. It's like 2. Okay, another way I could number this chain would be to number it 1, 2, 3, 4, 5, 6, 7, 8. Okay, now I've gone through all possibilities trying to figure out which one is going to give me the longest chain, and I've come up with 2 ways to get octane. Okay, so I had 8. And so I'm going to leave it as is, although you might have to reconsider and look for the lowest possible numbering. So we have some substituents here. We have a substituent at carbon 2. There's a methyl group, so we have a 2-methyl somewhere. We'll wait to add it in a minute. And on carbon 4, we have an ethyl group with 2 carbons. So that would be 4-ethyl. Okay, so I have all the parts now. I need to assemble it. Now we number them by alphabetical lettering, so the alphabet is the way we want to go, and ethyl comes before methyl. So 4-ethyl, 2-methyl octane is this structure. If you number it wrong, all right, let's talk about if you numbered this incorrectly. And I know it's getting messy, but let's assume that you numbered it wrong. Let's say you decided this was 1, 2, 3, 4, 5, 6, 7, and 8. And if you told me that this was 5-ethyl, 7-methyl octane, you would get the answer wrong because I can get lower numberings by numbering in the other direction. So this is not correct, and this one is. All right, let's name this structure. Again, I'll give you like a minute and a half to think about this for a second. All right, so we could start a number of ways in counting our longest continuous chain. But one thing I know is with this double bond in here, I'm almost certainly going to have that on my longest continuous chain. So we could count 1, 2, 3, 4, 5, and we'd be wrong because we can make it longer. So, oops, I'll just leave that one there. 4. I could come down here and say, oh, 5, 6, and 7. All right, and I could try numbering in a number of different ways, but you're going to end up with a hept because it has 7, and with this double bond, that makes it an ene, heptene, because there's a double bond in this structure. Now, I need to find my substituents. All right, so in this case, when you're doing double bonds, the lowest numbering goes to the double bond. And so I'm going to know that that is a 2-heptene because the double bond starts at carbon 2 there. Then I'm going to look for my substituents. So I have a substituent here with 1 carbon and a substituent here with another carbon. And so I'd call this 4,4-dimethyl, indicating there's 2 methyl groups, 2-heptene, indicating that the double bond is on the second carbon. It's possible you'll see 4,4-dimethyl, hept2-ene. Both of those would indicate. This is a better one when you have more than one for certain, but this indicates either way that the double bond is at carbon 2. Now, I want to write some formulas. Now I'm being given names. I want to figure out the formulas. So let's put 2,2,4-trimethylpentane together. So we need 1, 2, 3, 4, 5. Now you can practice turning these in space and turning them in different directions, but for right now, when you're starting to make these expanded formulas, just put in the backbone. Then you're going to come in and put in the substituents. So I'm told on carbon 2, and if this is, so be sure you number your carbons and know which one is which. So on carbon 2, I'm told that I have a 2-methyl and another one at the methyl, all right? And then on carbon 4, I have a methyl group. So if I was writing this in its form, I'd have CH3, and now I want you to look at this carbon. Carbon 2 has 1, 2, 3, 4 bonds already. So I'd say carbon, then I'm going to put in a CH3, a CH3 in parentheses, or maybe I'd put in, I probably wouldn't put that in because that kind of looks messy, CH3, 2, that indicates that those are substituents. CH2, CH, CH3, oh, running out of space. One more up here, CH3. So let's look at this, the way this is written. Of course, here's my CH3. I'll have to put on 3 hydrogens there. There's no hydrogen on the carbon 2, and that's because there's 2 CH3s or 2 methyl groups bonded to it. So when you see something that looks weird like this, that's a substituent that's gotten bonded. Then on the carbon 3, I have to have 2 hydrogens. Carbon 5 has to have 3 hydrogens. And carbon 4, okay, carbon 4 has a methyl group, and in order to make 4 bonds, or the octet rule work, I have to have another hydrogen. So that would be CH, CH3, CH, CH3, that indicates everything here on this carbon, and then And then I had to finish my structure up here. Here's my CH3 down there. All right, how about 2,2,3-trimethylbutane? All right, so this would be, I guess I'll do this one on another, well, I don't want to do that on a different page. I'll try and squeeze it in here. In fact, here, I'll take this off. All right, 2,2,3-trimethylbutane. So this time I need a 4-chain carbon. I'm going to put in a methyl group on carbon 2 twice and a methyl group on carbon 3. Then I'm going to fill in my hydrogens. This will have to have 1, 2, 3. This carbon already has carbon 2 already has 4 bonds. I don't need to do anything to it. Carbon 3 needs 1 hydrogen, and then carbon 4 needs 3 hydrogens to fulfill the octet rule. So in writing this structure in a formula, I would write CH3, C, CH3, CH32, in parentheses. That indicates that that's a methyl, 2 methyl groups bonded to that carbon 2. Then CH, CH3. That's our carbon 3 with a hydrogen and a CH3 methyl group on it, and then CH3. So you should be able to take a name and write it, and then tell me what its formula is in terms of its condensed formula. Now this one's going to be a little bit different because we haven't really done anything with the halogens yet, but they work very much like the methyl group, except we're going to be talking about bromine and chlorine. And notice that in these groups, it's named bromo something or chloro something. But at any rate, let's start by making we start at the end. We're going to figure out there's 5 carbons. So 1, 2, 3, 4, 5. Then we're going to determine that the double bond is at carbon 2, so I'm going to make a double bond here. Now I'm going to go in and I'm going to use my prefixes. I'm going to use my prefixes like so in order to finish this structure. So I'm going to start with the bromines or the bromo, and it tells me it's at carbon 4. Well, I already know this is 1, 2, 3, 4, 5 because I set this when I made 2, the double bond right here. So on 4, I'm going to have a bromine or a bromo and a bromo. 4, 4 indicate, and dibromo indicates there's 2 bromine atoms, and each of them are on the carbon 4. And then I have 2, 3 dichloro, indicating there's a chloro at carbon 2 and a chlorine at carbon 3. All right. Now, I need to come in and fix my formula, my hydrogens here, and so this will have to have 3 hydrogens to give this carbon 8 bonds, or 8 electrons. And then on carbon 2, I'm just gonna dot these because I'm tired of having to rewrite them. I have 1, 2, 3, 4. I don't need to do a single thing to that carbon. It doesn't need a hydrogen. It already has 4 bonds. Likewise, on carbon 3, I have 1, 2, 3, 4. That carbon is also already fulfilling the octet rule, so that's good. On this carbon, I have 1, 2, 3, 4. Already fulfills the octet rule. I'll leave that alone. And then I'll have to have some hydrogens down here at the end of the chain. So this would be your structure for 4,4 dibromo, 2,3 dichloro, 2-pentene. All right, so notice what we did. we start with the root, then we do the suffix, and finally we put on what belongs in the prefixes, and then after that you put in the hydrogens you need to make everything, all carbons have an octet. You know, I know I forgot something. I wanted to talk about this pattern, not this one. Not that one, although that's part of it. I wanted to talk about finding geometric isomers. I didn't really write it down specifically like I wanted to. So you start with a straight chain of however many carbons you're supposed to have. Start with a straight chain. Then you go down one, lose one carbon, and make it to a substituent. So instead of having the pentane molecule, we're talking now about the butane. We went down one and made a substituent here. After you found everything possible for the loss of one carbon and making a substituent, then you look to lose 2 carbons from your chain and make substituents. And you do this over and over and over until you get as many as you possibly can. Then you would start with your cyclic structures. See if you can make cyclic structures out of something. But we're going to leave off our cyclic structures for this class. Now, I'm sorry, I didn't mean to stop in the middle, but I wanted to tell you about that. And I was remembering because I was looking at this pattern. All right, so now I want you to be able to look at structures that I've given you, and I want you to be able to tell me what kind of hydrocarbon they are. Is it an alkene? Is it an alkyne? Is it an alkane? All right, so that means you have to draw things a lot of times. So let's draw this structure. So we can, and I'm going to leave the hydrogens off for the moment. I'm going to put on the 4-carbon chain that I see over here. And then, of course, all of this hydrogens, especially on the end, are going to be, for alkanes, 3 of them to make carbon have an octet. And then I look back at the structure, and I can see there's a hydrogen here and a hydrogen here. But when I look at these 2 carbons, this carbon and this carbon, they don't fulfill the octet rule. Now, you don't get to change and say, oh, that's CH2, CH2. Instead, if I've written it like this, I expect you to figure out that this should be a double bond. All right? That's how you're going to see that. So this indicates, when you see something like this in the middle of the chain, where you have a CH and a CH, that's going to indicate a double bond most of the time. So let's look at this structure. It has 5 carbons. 1, 2, 3, 4, 5. So let's put 5 carbons down here. 1, 2, 3, 4, 5. And we know that these outer carbons have hydrogens. It says so. And just to make our life easiest, we'll leave everything in the same order. That means this hydrogen has 2 carbons. And then we look over here, and we see that these 2 carbons have no hydrogens attached. So this set of carbons is really not doing well. It doesn't come anywhere close to fulfilling the octet rule. But if I make this into a triple bond, suddenly both carbons have fulfilled the octet rule. Now, what would I call this particular structure? Oh, I should probably name both of these. What is this structure? This first structure, if we number our carbons, 1, 2, 3, 4, this is 2-butene. What would this structure be? Let's number our carbons. 1, oops, better do it in a different color. How about black? 1, 2, 3, 4, 5. And so the name of this thing is going to be 5 carbon name is pentyne, indicating there's a triple bond there. So far, these are all valid, all right, as I've given them to you in this name. So let's look at this next one. This next one is, put it down here, 1, 2, 3, 4, 5. I'll put in my hydrogens. I'm tired of writing them, so I'm just going to make marks. And then I have an H here. Okay, so there's 1 hydrogen there and none on this carbon. So what am I going to do to give this, to make this a valid structure? I could make a double bond here. That would make this carbon okay, but what about that carbon? That's not good because this one doesn't fulfill the octet rule. Too few. That's not an octet. So how about if I redraw this? I'm going to leave the hydrogens off for a minute except the one I'm interested in, which is this one. Now, to make this, what if I make this into a triple bond? Well, now this carbon is happy, it's an octet. But what happened to carbon 3? Whoops, what happened to everything? Let's see. What happened to carbon 3 down here? Carbon 1, 2, 3. Carbon 3 has 5 bonds. There's the 3 in the triple bond, 1 to the hydrogen and 1 to this carbon. That's not valid. Neither one of these are valid. This would be a case where you wouldn't have a structure that fulfills the octet rule. This is not a valid structure because, remember, carbon always is going to fulfill the octet rule. So the only thing I can say is you've got to practice, practice, practice. So get out your book, look through those problems, draw those pictures, draw those carbons, input the hydrogens, see what you've got, what you need to do to correct problems, to name them, to number them properly. Whatever it takes, you need to practice, practice, practice. I think that's the end. Oh, no, I did want to go over these rules. So you may want to look at your book because these are kind of not very clear, I know. So you name the longest continuous chain. That's your first job. First thing you got to do is figure out, even if they turn in space in every which direction, which is the longest continuous chain. And then, of course, you'll pick out the right root. Hexane is this one. Hex. Then you find the type of compound, okay, for an alkane, where every carbon has 4 bonds. Every carbon always has 4 bonds. Where every carbon is singly bonded, that's going to be an ane, single bonds. And remember, when it's a double bond, it's an ene. When it's a triple bond, it's an ine. And then, of course, there could be some kind of cyclic structure. For example, we might have cyclohexane here, cyclohexane, which we looked at in the last lesson. Then, in this particular case, they're giving you some substituents. So this was their longest chain. I want you to notice, we could have also, just FYI, counted this as the longest chain because both of those are 6 carbons. But we'll stick with what they did. And so when you're counting, which direction do you want to count? From the lowest possible position. So 1, 2, 3, 4, 5, 6. And so we're going to say we have a methyl on the carbon 2 and an ethyl on the carbon 3. So in this case, I showed you methyl, ethyl, methyl. Ethyl because it comes first alphabetically, and methyl comes second. And then you have to number where they are. So in this case, the ethyl group is on carbon 3, and the methyl group, alphabetically though, is on carbon 2. So this is a 3-ethyl, 2-methyl hexane. So name the root, name the ending, the suffix, and then number everything and make sure that you get the lowest possible numbering. Then when you're naming it, it goes alphabetically. Now, what if I have, I'm going to change this just a second here, and let's assume for just a minute that I have another ethyl group here. And what we would call this is, this would be on a 2,2-dimethyl on this particular carbon. Okay. So no hydrogen here. And then I'll still have my ethyl on group 3, 3-ethyl. Now, does this mean, do I have this right? Di, in terms of alphabetically, di comes before E, so it seems like that ought to be true, but we don't count the number of how many there are. In this case, we would call this 3-ethyl, 2,2-dimethyl, even though D comes before E, it's the methyl group we're interested in, hexane. And that dimethyl hexane is all one word. So once again, practice, practice, practice.